Assalamu alaikum, dear students. Bismillahir Rahmanir Rahim. Welcome you in lecture. I think so. This is lecture 13 or 14. Okay. So, in this lecture today, inshallah, we will cover a very unique problem. Clear? And this problem is basically based on, you can say, an inclined member. Although it is a simply supported beam, having a hinge support is there and a roller support is there. Clear? So basically there is a little bit, you can say, change uh, in modeling of this member, as well as assigning the load, as well as assigning this joint. Okay. So before starting my starting to solve to analyze this beam, you must need to understand that what is local axis and what is global axis. Okay, global axis, you see that there is at this origin point or at this origin point x, y, z. These are global axis. Global axis basically, these are those axes which is, you can say, which is constant for each and every element in joint. Okay, in SAP basically you must know about element, you must know about joint, you must know about area section. Okay, point, node. So element is basically, column, beam, cable. These are basically known as line element. Okay, because its length is very large as compared to its width and depth. Clear? So therefore, whenever we are modeling them into say 2000, we assign these column, these cables, these beams as line element. Okay, and area section is basically slab, shells. Okay, if you if you if you see to the dimension of, slab, so basically the slab has a width and has a length. So this has a basically, you know its length and width has a certain ratio. Okay, has a certain ratio. So this is its width and this is its breadth. So, and its thickness, we ignore here its thickness because its thickness is very small. Okay, as compared to its width and its breadth. So therefore we ignore its thickness and we assign the slab or shell, okay, as an area section. Similarly, the joints, which is right there, these are called as node. So node are the points, where the elements are area sections, they are separated. They are, when we select it, okay, the members, the selection is, you can say, is individual. The selection is separable. So therefore, you must know about these terminology. These terminology basically used in uh, SAP 2000. Clear? Now, global axis is basically, or the axis which is, which is constant for all elements, for all joints. Okay, uh, and local axis basically, these are different. These are different for each joint. These are different for each element. These are different for, each node. So therefore, we can see that there is a little bit difference. So, for example, this AB, we can see this is a beam. Clear? So this beam has our local axis, that is will be seen once we assign those local axes to this beam, will be somewhere there. Okay, so basically this is the local axis for this beam, and similarly for this joint you will see that there will be their local axis, and similarly for this joint there will be their local axis. Clear? So you must know about the local axis, you must know about the global axis. Okay, and the global axis is basically constant. Okay, and they will be, they will be shown at this joint, or at the middle of the beam. Clear? So if the global axes are there, okay, global axes are there. Clear? Now all the points of the structure, you can say, uh, are located with a reference to the origin of global axis. Clear? We cannot change the global axis. These axes are constant. Clear? But the local axis is basically, you can change, you can rotate, you can, okay, you can do anything you want. Clear? So, and the difference between local axis, once you assign, how you can differentiate between these two. So the global axis is always, it is denoted with yy, with z, and with x. Clear? And similarly, if you assign the local axis, they will almost representing by small x, small y, sorry, this small z, this small y, and small x. Clear? Or mostly, always you can say it is denoted by, by 1 1, by 2 2. Clear? And by 3 3. Clear? By 3 3. Almost, it is denoted by these 1 2 3. Clear? So you must, you must know the difference between local axis and global axis. For example, if I assign, let's say I will show you these axes in later. Okay, now we will start the that how we will model this beam. This beam, now we will model by using the frame command, 2D frame template. Okay, we can model them by axis as well. We can model it by, let's say we model it by grid spacing. Clear? So 24 feet, there is x1, there is x2. Clear? You must know that there is x1 and there is x2. Okay, so x1 and x2, and there is this is z axis, so this is z1 and this is z2. Okay, and we don't need y. Clear? Because in y direction there is, we ignore the width of the section. We basically take the height of the beam. Okay, because from horizontal axis the beam is located at a distance, at a height of 10 feet. This point is basically a height of 10 feet. So now the distance between z2 and z1 will be taken as 10 feet, and the distance between x1, okay, and x2 will be taken as 24 feet, and the inclined length of this beam will be, using the Pythagoras theorem. You will see that 10 square plus 24 square comes out to be 26 feet. This will be its inclined length. It is very, very important. And you must know that this hinge joint, let's say I will explain this in later. Okay, so let's say this is we select the proper units, make sure your units are okay, clear. Kef feet, clear. So kef feet, select the kef feet here, new template, and let's say we assign this by global, by grid spacing. We have two axes in x direction, and we have one axis, let's say in y direction, but we have two axes in z direction, clear. The distance between x1 and x2 is 24 feet. The distance between y1 and y2, we ignore it, let's say this is 1, and the distance between z1 and z2 is 10 feet. I expand these points, clear. So let's say now, make sure you will be in xz plane. So this is a kind of rectangle, and we need to you know we need to locate or model the beam this in this uh, in this rectangle. So select the line element, click here and click here, clear. This will be now your beam. Okay, this point is located at the global axis. These are global axis, clear. These are global axis. 0 0, this is the origin point, and this point will be located at a 24 feet and 10 feet height. So their coordinates will be 24 and 10. So see there, 24 and 10. So this is okay. The location is okay. Now we need to assign the joints. We need a hinge joint at this point. So this is a hinge joint, and its direction is in this direction. Okay, and we need a ruler support there, clear. This is a ruler support, clear. Now one thing you make sure, no, I want to see you the local axis. So just press this button, okay, and here you select local axis and okay. You see there, you see this is the local axis up for this joint, and this is the local axis for this joint, the red one, clear. uh, Always it is, the x is basically denoted with a red color, clear. So it shows that these are the local axis. Now one thing you must know, that at the initial stage, once you assign the local axis with to the members, these are just you know in those direction in which the global axes are, means the local axes are basically parallel with the global axis. But in later stages we can change, we can rotate, we can move, okay, the direction of these local axes. So let's see here. Basically you see that the support, the ruler support which is right there, it is in vertical direction. Its axis is basically vertical to the, or you can say perpendicular to the beam, and we model the ruler support in this shape. Now we need to rotate. Okay, there it is in this direction. We need to rotate because this is its xz, and this is its x. These are its local axis, which is which is parallel to the global axis. This is global axis x and z. Clear? Now we need to rotate. This is its y-axis. We need to rotate these axes by an amount of which is equals to which brings the these local axes perpendicular to this member. I What I mean, that these local axes will become in this shape. X comes here, z come here, and y come here. Clear? So we need to rotate now these local axes or this joint. So how we can do? We select this joint, assign joint, because we are rotating the joint, therefore we select joint. Okay, local axis. Now here it says through which axis you are rotating your joint. Now you see that basically you see that we are rotating, we are basically rotating the element, about the because this is your y axis, this is your z axis, and this is your, now the joint is basically in this shape. Clear? The joint is this shape. Now we need to rotate this joint uh, to make it perpendicular to the beam. Okay, now we need to rotate this element about y-axis. Okay, about y-axis. Clear? Now what will be the degree, that how much degree we need to rotate this element, how much degree we will rotate that this joint will become perpendicular with this beam. So you need to determine this angle, and this angle will be equals to theta equals to tangent inverse, clear, and perpendicular divided by base, means 10 divided by 24. Its roundabouts comes out to be, I think so, 30 degree. Clear? So this will be around about 30 degree. Clear? So let's see how we will rotate. Now the rotation is about y-axis. Okay, and one thing you must clear, that the rotation is there basically start from z-axis, or you can say x-axis. So we have to rotate it anti-clockwise, not clockwise, anti-clockwise. So therefore we insert a negative angle. Okay, so now we see that the local axes are rotated, although the global axes are in same direction, and the you know the if you in 3D you see that the local axis of this joint that is by red color is perpendicular to the global axis, but here you can see the local axis of that joint is now rotated, that is not in those shape in which the global axis. Clear? You see that now the joint axes are basically in this shape. Clear? Now one thing you must make sure that we need to rotate the local axis of the beam element. Okay, now if we assign the local axis to this, at the first instant, once you select the joint, you select the joint option. Now we will assigning the local axis of line element, so therefore you will select frame, and in frame you will select local axis. Clear? So there you can see we also need to rotate the local axis of this frame at a 30 degree, because you can see this loading, the loading is perpendicular to this beam section, so therefore we need to rotate the local axis of the beam as well. Here you must know that the local axes are in this shape. Okay, now we need to rotate the local axis of the beam to apply the, if we don't rotate the local axis of the beam, the load will not be applied in perpendicular direction. The load will be applied So one thing you must make sure before the rotation of local axis of a frame element, in this case basically, or a line element in this case is basically, you must need to bring the local axis of this line element. How to bring the local axis of this line element? You just check this button, and here you can see frame, cables and tendons. You press this local axis and OK. Your local axis will be right there. OK, they will be representing there. OK, or you can say they will be shown there. OK, so these are the local axes now of this line element. You see that the global axis, this is x, y, z, and y direction is passing through the screen. Now you see that these are the local axis of this line element. X axis is, along the line element, y axis is perpendicular to the line element, and z axis is passing through the screen here. So they are different, or you can say they are different from the global axis, as well as they are different from the local axis of this joint, because the z axis is now here is perpendicular, where the y axis is perpendicular there. Okay, and there the local axis of this line element is passing through the screen, where in this case the y axis of this the local axis of this joint is passing through the screen. So this is the difference between local axis and global axis. Now if you don't want to rotate this line, the local axis uh, of this line element, you can apply loading to this element as well, because you see, look here, you need to identify the proper axis, through which axis I have to apply the loading. You see that the z axis is perpendicular to the screen. Z axis is perpendicular to the screen. No, if I apply my loading perpendicular, or you can say parallel to my z axis, the load will be perpendicular to the screen of my laptop. And similarly, if I apply the loading perpendicular or parallel with the x axis, the loading will be parallel with the line element. The only way that is my y axis, because my y axis is perpendicular with the line element. So if when I assigning the load to this line element and I select the y option, my load will be perpendicular to this line element. Okay, if I don't rotate my axis, okay, and let's say my local axis in this direction, clear? Let's say my local axis, like in this shape, this is z, this is y axis, and this is x axis. If I don't change, let's say I select the gravity direction and I assign the load to this line element, the load will be somewhat in this pattern, and I don't need to assign the load in this pattern, because the load is perpendicular to the element. I need to assign the load perpendicular to the line element. Okay, perpendicular to the line element. So for that purpose, I need either to identify the local axis first of all, and then if the local axes are not perpendicular to the any of the local axes, there may be x, there may be y, there may be z. If any one of the local axes is not perpendicular, then I rotate my local axis to make perpendicular either one axis of the local axis with the line element or frame or beam. Okay, so there I don't rotate the elements. I identify my local axis and I see that my y axis of the local axis is perpendicular to the line element. So I can assign my load now in perpendicular to the line element. So select it, assign, and frame loads and distributed load. Clear? Make sure your dead load multiplier will be 0. Okay. Okay. Now your units will be kept your this one, and here you will select the global axis, local axis, sorry, not global axis, because we are assigning load with a local axis. If you select the global axis, and the load will be, you can say, parallel or perpendicular with this global axis, not with this local axis. So therefore you need to select the local axis. Now the load will be assigned with the local axis. Now here you need to identify, because the local axes are representing by 1, 2, 3. Now x is basically, I think x is basically for 1, 2 is basically for y, and 3 is basically for z. Okay, this is change. This is change for local axis. In for global axis, x 1 is for x, 2 is for z, and y is for basically y is for 3. Okay, but in local axis 1 is for x, 2 is for y, and 3 is for z. So therefore I select 2. Okay, let's say try. Select this option and apply now loading. So in loading you can see that at a distance 0 the load is 5 kgs per feet, and at a distance of inclined distance you need to insert inclined distance, not horizontal distance. At a distance of 26 feet you have a loading intensity of 2 kg per feet. So let's say at a distance of 0 you have and make sure you will be insert the value with -5. -5 means, because y axis, here I am selecting y axis, that is 2 2, is is acting away from the beam. You can say that is to upward, that is not toward the downward direction. So therefore I will insert a negative sign. 26 feet, and there is intensity -2. Clear? So this kind of assumption, selection, absolute distances, and all thing is now okay. So this is the load. You see, if you don't identify the proper local axis, okay, that which one of the local axis is perpendicular to my structure, then you cannot be able to select the proper loading. Okay, and you must identify the difference between local axis and z axis, and the representation of 1, 2, 3. And global axis, you must know that for x axis we use 1, 1, for y axis we use 3, 3, and for z axis we use what? 2, 2. While in local axis, basically you must know the difference. For in local axis, x 1 for x, 2 for y, clear, and 3 for z. You must know this difference. And in rotation, you must know that whenever you are rotating this element, to which axis I am rotating my joint or my element. Clear? And you must note that when I insert a degree, an angle, so you need the sap2000 rotate the element. It starts degree from z. It assume that z equals to 0 degree, and it starts in a clockwise direction. Okay, so you must know this difference. I will use this command in later stages. Okay, so you must differentiate between these kind of things. Okay, and you must know about, okay, because we have in frame structure analysis, basically we will rotate these joints and elements. Clear? Now we are assigned proper joints. You check the beam, Your beam is now properly modeled in your SAF, and now you are ready to analyze. Clear? Model do not. This is, I think so, lecture 14. So, clear? So, I think your reactions is now right. Okay. Okay, because if you see there, your by is 39, so I have 39. Ay is 48, so ay is 48, and x is basically uh, is roundabout. This is 39, this is 50, and this is close to, you can say, 20. This is 20. Okay, this is basically there it is 20, but we are close, round about 16. So this is not great difference. Okay, save give you a little bit difference. Okay, so this is acceptable. This one is okay. Okay, and this one is also okay. So this is a kind of procedure you can check out the shear diagram as well. Okay, and you can check the reaction as well, and you can check the movement diagram as well. Clear? So this is the movement diagram, and that will be your. You must note the difference that there the bending moment curve is linear, but actually you can see there the movement diagram curve for a very young load, I think so it is 3-degree curve. Okay, so you must know this difference. Clear? So this is the procedure for analysis of an inclined member. I hope you will learn about this video. If you have any question, any doubts, you can share with me. Okay, and thank you.